Hello and welcome everybody. Today in geometry we will be discovering a new chapter, chapter 9, which is going to be on parallel lines. And how is that going to play in with all the stuff that we learned about angles and also possibly congruent segments. So first we're going to have to define some things, and that's just very general for the most part for any new chapters. So here you can see that we're going to go ahead and define the following terms. So we'll go ahead and do that first, and then afterwards we are going to introduce a few theorems. Actually, it's just going to be the second one right here. The first one that's going to be left probably in this next section. All right, so here is the first part then. In space, if you have any two lines, there are three possible things that can actually happen. So keep in mind that this is not 2D, but 3D. So this is just kind of like in a room, for example. In case number one, you can have the two lines intersect each other. So you can see that is exactly what's happening there. So line 1 is going to intersect line 2, and the intersection is going to be some point x then. So that means that those two lines are going to be coplanar. Now, in case 2, the two lines could be in the case where they do not intersect each other, and they are still coplanar to each other. So, for example, if you take a look at the edge in your room on the top of the ceiling and then the edge on the bottom of the ceiling, notice that those two lines are not touching each other, but there is a plane that's going to contain them then. And then in the last case, if the two lines are not going to be touching each other, but in this case, the two lines, they actually are not coplanar. So this is a little bit hard to see, but what is happening here is that you have line 1, which is not intersecting line 2. And keep in mind, once again, that this is 3-dimension. So that's why you can see that little space in between where I'm showing that they're not actually touching, because it is possible for that to happen then. And again, if you look at your room, there's definitely like some edges that are not going to be coplanar, and they are not going to be intersecting each other. So the first case we've seen plenty of times already, because we talked about how two lines are intersecting each other and coplanar and so forth. But it's the second case and the third case that we're actually going to focus on in this chapter. The second case, where if you have two lines that are going to intersect each other at an empty set, and they are two that are coplanar to each other, then we can say that the two lines are what is known as parallel to each other. And you can see that there's like a special symbol underneath for parallel, which is used by two dashed lines over here. So that is to indicate that line 1 is going to be parallel to line 2. Now, the third case over here, while it is interesting, we're going to probably come back to it in a little bit, maybe like say in a distant future in a different chapter, where line 1 and line 2, they do not intersect each other, and line 1 and line 2 are not coplanar. These two lines are what is known as skewed lines. So this is an example that, if two lines are not intersecting each other, they don't necessarily mean that they are parallel, because one could be the case that they could be parallel, the other could be the case that they're skewed. It all depends on if they are coplanar or not. All right, so our focus is basically going to be in case number 2 right here, where two lines are going to not intersect and going to be coplanar. So this is the parallel thing that we're talking about. Okay, so here is the first theorem, which states the following then. In this theorem, it says that if two lines are parallel to each other, so they are coplanar first place, then there is exactly one plane that is going to contain them. Now, once again, you can see the word exactly one or only one. So that means that you are going to prove existence and uniqueness, meaning that there should only be one in this case, not 2, not 3, and so forth. All right. So what we're going to do is we're going to go ahead and prove according to existence and uniqueness then. Well, the existence part is actually pretty easy, because by definition of parallel, line 1 and line 2 are coplanar, right? Because by our definition previously, you can see that there is a plane that's going to contain both of them. Now for the uniqueness part, now this part is going to be a little bit hard to swallow, but I think it's not too bad. So we're going to go ahead and assume that there are two planes, we'll go ahead and call P1 and P2, that is going to contain both line 1 and line 2. Now, that sounds kind of weird already, but, that's how it works. Because remember, if you're doing a uniqueness, you usually do an indirect proof. So we're going to go ahead and, just draw like a quick picture of this so you can see how that works then. So let's say, let me go ahead and erase that, kind of messed up a little bit. So let's say in this picture over here on the right-hand side, there are two planes that contains these two lines. So here is line 1, and then here is going to be line 2. So you can see plane 1 is going to be this case. And at the same time, there's going to be a second plane that is supposedly going to contain them too. So we're just going to kind of like overlap it like this in this case then. Okay, so we'll call the red, go ahead and call it plane 2 then. So that's exactly what we have. Now, what I'm going to do is I'm going to go ahead and go to one of the line, and line 1 is the line that I'm picking, and say that let point X be a point that's going to be on the line. So there is a point definitely on the line, and we're just going to go ahead and call it X. Now, what that means is since X is going to be on line 2, it is going to be on both planes. So we can say the following then. Then X and line 1 are going to be on plane 1, and then X and line 2 are going to be on plane 2. And that right there, unfortunately, is going to be, well, not unfortunately, but is fortunately going to be our contradiction. Because if you remember, there's a theorem back in chapter 3 that says that if you have a point and you have a line, then there is exactly one plane that is going to contain both of them. Well, in this case, there are two planes because there's plane 1 and plane 2, and that right there contradicts that theorem that we have back in chapter 3. All right, so there it is. That's going to be theorem 9.1. And this right here, there's no name to this theorem, so that means that it's going to be kind of like a stepping stone that we're going to be using to prove something that is more important in the future. So let's go ahead and move on for right now. Okay, theorem 9.2. This one says that if you have a plane, and then if those two lines that are in their plane are both perpendicular to the same line, then the result is that those two lines are going to be parallel to each other. Well, as a restate, here's what it looks like then. On a plane, if L1 is perpendicular to L3 and L2 is perpendicular to L3, just like it's showing on the picture on the right-hand side, then the conclusion is that L1 is parallel to L2. Well, we kind of did this in the past back in chapter 6, but now it's going to be official. So we're going to go ahead and be able to use this as a theorem. Now, the only way that we can deal with proving something is parallel, we have to kind of go by the formal definition, right? Parallel means that you have two lines that are coplanar, which is in this case, that are not going to intersect. So we're going to have to do this indirectly. We're going to go ahead and say, let's just go ahead assume that line 1 and line 2 are going to intersect at some point P then, somewhere out there. So here, if I can kind of like draw in my illustration, I'm going to go ahead and kind of skewed line 1 so you can see that it's going to quote unquote supposedly intersect with line 2, and that intersection is going to be some point P. So that's going to be our indirect proof. If I can show that this case is impossible, that means that we did it indirectly, and we are going to be able to say that line 1 is parallel to line 2 then. Is this the only way to prove parallel lines? Not necessarily. In fact, we're going to find some easier way to do that, but for right now, this is all we have as a tool. Now, you can probably see already in this picture that that is impossible because by definition, that means that PAB and PBA are going to be right angles. So in my picture, I'm going to go ahead and draw some right angles right there because they are supposedly perpendicular to the same line. And that right there is impossible because remember, in any triangle, you cannot have two right angles. So that is going to be a contradiction of that theorem back in chapter 6. So there you go. That's going to be our proof then in this case. Okay, moving on to the next part, we're going to use all of that and use it all together to get our big proof, which is going to be coming up very, very soon. So kind of bear with me for a time right now, okay? And theorem 9.3, now this line, this one is actually going to be something that's similar to what we did back in chapter 6, which is to say, if you have a point that is not on the line through an external point to the line, there is exactly one line that contains the point that is also parallel to the given line. So here you can see in the picture on the right hand side, that's what I have. You have a line over here, which we're going to call L1. You have an external point, which is going to be P. What this theorem says is that there is exactly one line that is going to be containing P, and it's going to be parallel to L1. So that is going to be our picture. Back in chapter 6, we proved something similar in the sense that through an external point, there exists exactly one perpendicular. Well, in this case, there's also going to be one parallel. Okay, so the proof of this one is actually a lot easier than back in the old days of having to prove this. Yes, again, we also have to prove existence and uniqueness, but the proof that we're going to be using allows us to do both because we did actually a bunch of proofs already that dealt with existence and uniqueness. So here's what's going to happen then. We're going to go ahead and first say, let's go ahead and introduce a line that is going to be called L2, such that line 2 is perpendicular to L and containing the point P as a result. So going to the picture on my right hand side, let me just go ahead and erase that quote unquote parallel line. Let me just go ahead and draw that line that we just introduced. That's going to be this guy over here. And we can do this because back in chapter 6, once again, if you remember, there exists exactly one perpendicular to the given line containing the external point. So that's Theorem 6.3. So we know that this is going to be a right angle right here. And let me just go ahead and draw it with this pen right here so you can see that then. Next, what I'm going to do is I'm going to now go to line 2, right, and where point P is, and I'm going to do another something similar. I'm going to introduce another line, we'll call line 3, that is going to be perpendicular to the line that we just drew, and also containing point P. So then that means that in terms of where our illustration is, here is point P once again. I am going to draw a line that is going to be perpendicular to L2. So you can see it's going to go this way then. So that line that we just said is going to be this guy over here. And we're going to call that line 3. And this one is going to be using Theorem 6.1, which says that through an internal point, there exists exactly one perpendicular. So first we use the external point, then we use the internal point. And if you remember, they're both uniqueness. So that means that there's only one line of each that can exist. Well, now that we have everything, if you think about what we just proved earlier, right, we can now connect the dots. Because if you look, we have L1, which is perpendicular to L2. L2, which is perpendicular to L3. So then by the previous theorem, which is Theorem 9.2, then we can say that L3 is going to be parallel to line 1 then. So over here, let me just go and write that. So by Theorem 9.2, we can conclude that L3 is parallel to L1. All right, so you can see now we are actually using all the previous stuff to help us prove the current stuff. Okay, is this the end game? Unfortunately not, because this one, while it seems like it's kind of useful, we have something else that's definitely a lot more useful. All right, but before we go into those, we need to define a few more things actually, and this is now going to allow us to put everything together then. All right, so here's the first one, which is going to be a definition. Okay, so in this case, we have to define something over here that's called a transversal. A transversal of two coplanar lines is the line that intersects them in two different points. So here, let me just go ahead and draw what the transversal is. So let's say that you have two lines on a plane. So over here, maybe like say L1 and L2. Two lines that are not going to intersect each other, may intersect each other. I don't know. They're just two different lines. T is going to be a transversal if it intersects both of the lines at two different points, like over here. So you can see that line T, that is going to be called a transversal because you can it intersects both of those lines, but at two distinct points rather than one distinct point. Okay, so that's how a transversal works. Now, what's so interesting about the transversal? You'll notice that they form quite a few angles. The ones that I care about in this case anyway, for the time being, are the ones that are inside over here. Let me go ahead and label them. 1, 2, 3, 4. There is some sort of relationship for them as soon as certain, if there are certain conditions that are met. But we're going to go ahead and give them a name first, okay? So that's our next definition, which is going to be called alternate interior angles, or AIA for short. Okay, so two angles are considered alternate interior angles if the two angles are on opposite sides of a transversal and they do not form a linear pair. So in our illustration on the right hand side, you can see that I have 4 angles. Now first, the alternate interior angles comes in pairs. So that means there has to be 2 angles that are involved when you're talking about alternate interior angles. First of all, we're going to divide them by the transversal. So that means that we're looking at 1 and something that's on the opposite side, or 3 or something that's on the opposite side. Now, if we look at 1 and 2, that doesn't work with our definition because you can see how they form a linear pair, and that's not what I want. Nor can I choose 3 and 4 because they also form a linear pair, even though they're on opposite sides. So what that means is that 3 and 2, those are going to be alternate interior angles then. Just like number 1 and number 4, those are going to be my alternate interior angles then. So again, the definition is that they have to be on the opposite sides of the transversal, which they are, but they do not also form a linear pair. So they have to be kind of like opposite of each other then. Okay, so just to kind of reiterate one more time, let me just kind of draw a picture on the bottom one more time. So let's say we have L1, L2, and then we also have T right here. So if I call this A and B and C and D, then that means that A and B are alternate interior angles, just like D and C are alternate interior angles then. Okay, D and A are linear pairs just as usual, and C and B are linear pairs just as usual. Now, what's so interesting about these alternate interior angles in transversal? Well, this is where the parallel thing comes in because I feel like there's going to be a connection if those 2 lines are actually parallel. Well, let's move on to the next part then. Here in this next theorem, it says that in theorem line 4, if you have 2 lines that are cut by a transversal and a pair of the alternate interior angles are congruent to each other, then the other 2 alternate interior angles are going to be congruent as well. So that is to say, in this picture, if 1 and 4 over here are congruent, then they're saying that 2 and 4 are also going to be congruent. And I think you can probably figure out how to do the proof for this because if you remember, 1 and 2 are linear pairs and 3 and 4 are linear pairs. Going back to chapter, I think it was 3, it says that if 2 angles are congruent to each other, then their linear pairs are also going to be congruent to each other by the supplement theorem. So that's going to be our theorem 9.4 then. Now let's go ahead and put it all together and see what is it that we want out of all of this. And this is the main entree, I suppose you can say. So this theorem 9.5 is the one that we're going to be keeping out of all of this. Here is what it says that if you have 2 lines that are cut by transversal and 1 pair of alternate interior angles are congruent, then the 2 lines are going to be parallel. So now you can see how everything comes into play because we are now talking about parallel, we're talking about transversal, we're talking about alternate interior angle. So let me just do a quick restate. So here they're saying that if you have 2 angles that are going to be alternate interior and they are congruent to each other. So for example, 1 and 2 are congruent to each other. Or it could be the other way around. It could be 3 and 4 are congruent to each other. The result is that if they are congruent to each other, then line 1 and line 2 are going to be parallel. So this is now going to be our very first way to show 2 lines are parallel without having to do an indirect proof. All right, so here's the restate then. If T is a transversal for line 1 and line 2, and angle 1 is congruent to angle 2, or it could be angle 3 is congruent to angle 4, then the result is that line 1 is parallel to line 2. So we're going to go ahead and do the indirect proof thing one last time, and from here on out, then you can just go ahead and use this theorem to prove 2 lines are parallel as long as you have the setup then. So what we're going to do is we're going to do an indirect proof, as we said. We're going to assume that line 1 and line 2 are going to be intersecting at some point x. Now, just to draw it on the side so you can see how this works. So here's line 1, right? And then here's line 2, and I'm going to draw it like this because assuming that they are going to intersect each other. So I'm going to show that this is an impossible situation. Now, T is going to be somewhere over here. So here's your transversal. Here's again 1, here is 2, here is 3, and then here is 4. Now remember, in the given, we're told that angle 1 is congruent to angle 2, just as angle 4 is congruent to angle 3 because of the previous theorem over here. So you can see that the squared angles, those are going to be congruent, and then you have the circled angles are going to be congruent. Well, if they're all congruent in that way, then what that means is, remember how 1 and 4 are related and how 3 and 2 are related. They are supposedly going to be linear pairs. So what that means is, hey, if they're linear pairs, then that means that 3 over here, that has to be a right angle then, because these two are going to be congruent. Just like these two right here are going to be congruent then. And then you have a right angle. Well, that, as you can see, once again, is not going to work because we can't have a triangle with 2 right angles then. So as a result, because we have a bunch of linear pairs that are all congruent to each other's, then you're going to have 2 right angles, and that is not going to allow me to have this situation as a result. So there it is. Now we can go ahead and show 2 lines are parallel to each other then by using this alternate interior angle theorem. So the reason why we call it AIP for short is that AI stands for alternate interior, and then P stands for parallel. So if you have 2 angles that are alternate interior angles and they are congruent to each other, then you can prove parallel. Now, thinking ahead a little bit, then that means that maybe there's something that's called PAI, meaning if 2 lines are parallel to each other, I'd like to think that their alternate interior angles are going to be congruent to each other as well, basically the converse of this. So we'll go ahead and save that for next time, but thank you so much for watching. I will see you next time then. All right, take care. Bye-bye.